this assessment, we're asked to predict which alkyl halide will undergo a faster SN1 reaction. Recall that the rate determining step of the SN1 reaction is formation of the carbocation. And so when we're comparing a secondary alkyl halide to a tertiary alkyl halide, what we're really asking is which is going to make the more stable carbocation intermediate. Well, let's draw the product of that first step. Again, we're only worried about the rate determining step here. The first step would give this, which is a secondary carbocation of this reaction. Bromide leaves to give a secondary carbocation. For the one that's tertiary, it will be slightly different in that it will now instead produce a tertiary carbocation. We know that the tertiary carbocation is more stable, and so our expectation is that the tertiary is going to be the faster reaction. How can we justify that on a reaction coordinate diagram? Well, we're going to make an assumption that the two start at approximately at similar levels. Maybe not exactly true, but it helps us tell the story here. So for the secondary, it's going to be an uphill process to make a carbocation. So carbocation formation is going to be uphill in both cases. Here we make the secondary carbocation. If we do the same thing in orange for the tertiary, again, having it start at the same place, it's going to start here, but it's going to finish lower because it's making a tertiary carbocation. The Hammond postulate tells us that the transition state is going to look like the product, and so this reaction will not reach as high a level as the reaction of secondary did. As a result, we see that the activation energy for forming a tertiary carbocation is going to be less than the activation energy for forming a secondary carbocation. The tertiary alkyl halide reacts faster in the SN1 reaction.